Hey, folks. Okay, so okay, so we can start. Hope you're all doing okay. Eventually, spring will arrive. All right, so we finished chapter 14. Um, we're going to start chapter 15 today, multiple integrals. So let me review again the analog in one variable. So so again, our setup from chapter 14. We have functions of several variables, right? So we have a function defined on some domain D, which is an Rn. And we've seen various notions. We've seen the notion of the graph, obviously. We've seen notion of domain, and most importantly, notion of partial derivatives, their interpretation, and in particular, we saw a very fundamental result, the chain rule. And we also just saw the notion of directional derivative, which is a generalization of the partial derivatives. And finally, we saw the notion of gradient and some applications, some fundamental properties of the gradient. Okay, so this, in a sense, would correspond to what we saw in Cal 1 for the one variable case. And what we'd like to do now is to move on to Cal 2 and talk about the notion of integrals. Okay, for functions of several variables. Now, what I'm going to do, the plan usually is to deal with the 2 and 3 variable cases, but this time around, we're going to stick to 2 variables. Okay, so for this course, I'm not going to go to 3 variables or more. Okay, so only 2 variables. Okay, one thing is that, in fact, there's not much difference, in fact, between the 2 variable case and the higher dimensional cases. So the definitions are basically the same, but I'm not going to go there. Okay, so we're going to stick to 2 variables for the rest of the semester. Okay, so for now, what I want to do is admit somebody else. There you go. Welcome. Is to briefly go over the 1 variable case for integrals, and then define for 2 variables the analog. Okay, so today, review of what's called the Riemann integral. In 1 variable. And then the definition in 2 variables. Okay. Okay, so Here we go. Okay, so why is it called the Riemann integral? So the notion of integral had been known since Newton and Leibniz, but formally it was properly well defined first by Bernard Riemann, German mathematician, 19th century, a student of Gauss. There are more general versions of integration, like the Lebesgue integral. If you do some math next year, in the next couple of years, you will see the Lebesgue integral. So when I talk about integration here, it's the Riemann integral, the one that you've seen in Calc 2. Okay, so one variable. Okay, so what's the idea? I have a function f, which is defined on some interval AB. And the idea is what we'd like to do is to define properly the intuitive notion So we want to define the intuitive notion of area under the curve. Under the graph, right? That's what we want to do. As you recall, what we're going to do is to define a signed area, right? So in fact, what we're going to get is a signed area. And by this I mean, and you'll probably remember this, that if you look at the function's graph, let's say it looks like that, from A to B, that the area on top will count as positive, and the area below the x-axis will count as negative, right? But once I get to two variables, I'm going to make the picture so that everything is positive, so it's easier to visualize and to understand. But keep in mind that the definition counts everything which is below the x-axis, or for two variables below the xy plane, as negative. Okay. All right. So the trick is this, basically, as you might recall. So the trick, or the idea, is to approximate the area we want by rectangles, right? And then you take a limit. Okay. So let's see how this works. So to approximate the area by rectangles, I need rectangles. So I'm going to cut up, so you divide the interval AB into n equal parts. And I'm going to give names to the division points. So A will be x0, and then there's be x1, right up to xn, which is B. Okay. And so my interval looks like this. I have A, I have B, x1, x2, x3, like that. Okay. And the length, so of the subintervals, is, well, the total length is B minus A divided by N. That's B minus A over N, and we call that delta X. Okay, so that's the length of our small intervals. Okay. Next step is to create our rectangles. Okay, and for this, I'm going to take some sample points inside the subintervals. Okay, so the second step is to take sample points. It can be any point, which will be called xi star. Xi star lies in the subinterval xi minus 1 to xi. Okay. And this is for I equals 1 to n. Okay. And now the rectangles will have height f of xi star. Okay, so each approximating rectangle has height f of xi star. And what's the base? It's the length of the subinterval, which is delta x, right? So each approximating rectangle has area f of xi star delta x. So just to picture this, let's say I have one subinterval here, xi minus 1 to xi. F maybe looks like this. This is the graph of f. Okay. And let's say xi star is over here. And then I look at this height like this. So the approximating rectangle is like this. Okay. Okay. And intuitively, if you take your subintervals very, very small, then the rectangle's area should be close to the area under the curve above the x-axis. Again, keep in mind this could be negative if the curve is below the x-axis, but let's just keep it in the back of our mind, but it's simpler just to talk about positive area. Okay, so now the sum of the areas of the approximating rectangles will be what we call the Riemann sum. So what is it? You take all the areas. What's the area of the ith rectangle? It's f of xi star times delta x, and you add them all up. So you go from I equals 1 to n. Okay? So that's the sum of your approximating rectangles areas. Okay? And hopefully, as you take n bigger and bigger and bigger, this thing should approach what we hope to be the area. Okay? And so we define the integral that way. Okay? So what we want is so that the limit as n goes to infinity, as you take your subdivision smaller and smaller, that this actually converges it. You have a limit. Okay? So that's our definition. So here is the definition. Okay, so we say f is Riemann integrable, or just integrable, if the limit as n goes to infinity of this Riemann sum of this approximating sum f of xi star delta x exists. Okay, so that's the definition of being integrable. We'll talk about, I mean, it's not, how would I say, it's not a big requirement in a sense. It's much weaker than being differentiable. So continuous functions, even continuous functions piecewise, are integrable. But you can come up with functions which are nasty enough not to be integrable. We're not going to go there. Okay. So if this limit exists, okay, so this limit is a number. So if the limit exists, this number is called the integral, or the Riemann integral. I'll just drop the Riemann here. It's called the integral of f from a to b and is denoted, as you know, by integral a to b f of x dx. I'll get back to that later, but the x here is completely irrelevant. We don't really need to write it. It's sometimes useful when you're doing things like substitution and things like that, but it's in any case. Okay, so this is a number. It's basically the sine area of the region which is cut between the x-axis, the graph of f, between a and b. Okay, all right. So now I want to refresh your memory. So if you're going to compute this, if you do it directly by the definition, as we just did, it's a mess, okay? So maybe you had a very, very cruel Cal 2 instructor who had you do tons of those with the limits and all that. It's even for very simple functions, this is difficult, okay? So this is difficult, okay? But we're very lucky. So usually what we do is use the FTC, use the fundamental theorem of calculus. So what does that say? It says that if you're lucky enough to know a function whose derivative is little f, then this is super easy to compute, right? So if we know some big F such that big F prime is little f, then how do you compute this? Well, you know, you just simply evaluate this big F, right? And subtract. Right? So this moves the problem to finding big F, and that's what you learn in part of Cal 2, is techniques to find antiderivatives, okay? So that's the reason. Okay, so what happens now? So that's, there you go, that's Cal 2, that was easy. So what happens when you have more than one variable? Well, it's not so bad. In a sense, the theory that I've just shown you is exactly the same, okay? So for more variables, it's basically the same. So I'm going to define it, but, and I'll get back to that right after I've gone through some of the technical details, but you'll see immediately there's a difference, even just in two variables. So think in two variables, say for two variables. So I have a function, and I'll look at the simplest case again, where the graph is above the XY plane. So what's the analog that we're interested in? It's the volume, right? So we want a signed volume of what? Of the solid between the graph of F and what? Okay, so here's the first difference. So for our functions, we had an interval. Okay, so in one variable, we had an interval. And now what do we have? Well, there's a lot more freedom in the domain that you can choose, right? So the analog of an interval would be a rectangle. And that's going to be easy. But even then, you want your rectangle to be parallel to the coordinate axes. If you skew it, already things get a little different. Okay, so first step will be to define the integral over rectangles parallel to the coordinate axes. So that's the first thing we're going to do. And actually, that's the only thing I'm going to do today, okay? So I'm going to do the definition of what we call the double integral, when the domain we're interested in is a rectangle parallel to the coordinate axes. And that's going to go through basically like the one variable case. On Wednesday, we're going to see how we can move this to different kinds of domains, okay? Because we'll be interested. So later, we'll need to do this over more general regions. Okay, it could be a disk, it could be an ellipse, you see what I mean, okay? All right, so today that's what I'm going to do, just this, okay? All right, so for now, basic definition over these rectangles. Okay. Okay, so here's our setup. I have f, a function. It'll be defined on a rectangle, which I will okay, well, let me try something. That's the best I can do. Is that better? Maybe not. It's not actually pressure sensitive, the pen. It's just, that's the way it looks. Sorry. I'll try to write a bit slowerly. Okay. Okay. So, okay. So F is defined on a rectangle, which I will write as follows. Okay, so this is a rectangle, but maybe we'll call it a big R like that. So what do I mean by AB times CD? This is the set of all XY such that X is between A and B, and Y is between C and D. Okay, so if I look at it from the top, and I'll pretend that everything is positive just to make it easier, but let's say A is here, B is here, C is here, and D is here. I'm looking at this rectangle here. Okay, so this is the domain over which I'm going to integrate F. Okay, so we want to define properly or formally again, this is signed volume of the solid which is bounded by the graph of F and the XY plane over rectangle R. Okay. So let me draw that. Okay. And again, I'm making the assumption just for the discussion here that everything is positive to make it easier. Okay. So here we go. So here's what this looks like. X, Y, I have my rectangle here in the domain, or it's the domain. That's R. I have the graph of my function like this. Okay. And the solid I'm interested in is this guy. Right? So the top is curved like this. Okay, hopefully you can see what this is about. Yeah, I can. Over here. Okay, thanks. Okay, so that's the picture. Again, I remind you, the graph could go below the XY plane. Those parts would be counted as negative, okay? But it's easier to visualize this thing and, where everything is above the XY plane, okay? So, okay, so here we go. The principle is exactly the same. So now I'm going to, so the idea is this, again. So the idea is to approximate using boxes, right? Rather than rectangles, now it's 3 dimensions. Parallelepipeds, so I'm gonna say boxes. Okay, so we're going to cut up our rectangle into small rectangles. Take sample points inside these small rectangles. That will be the height of each little box. We're going to add up the volumes of the boxes, take a limit, okay? Okay. Okay, so first step, I'm going to divide this rectangle. I'm going to do it in the x coordinates and the y coordinates. Okay, so subdivide the interval AB, that's in the x direction, into m equal parts. Okay, so A is x0, then I have x1, x2, right up to xm, which is b, okay? And delta x will be the length of these subintervals, so it's b minus a over m, okay? Second step of our big first step is to do the same in the y coordinates. Y coordinates, so subdivide CD into n equal parts. It doesn't have to be the same number of parts. Okay, so C is y0, then y1, right up to yn, which is d. Okay, and what I'll call delta y will be the common length of these subintervals, which is d minus c over n. Okay, so I'm going to show you a picture, again, seen from the top, of the rectangle and the subrectangles generated by this. Okay, so let's Okay. Okay, so here's the picture of our subdivided rectangle seen from the top. So let's say, so this is D, this is C, this is A, this is B. So I've subdivided this interval, I've subdivided this interval. So this basically creates a bunch of subrectangles like this. Okay? All right. So a few remarks about the subrectangle. So I have the big rectangle R. So the area of the subrectangle, we'll need that, right? We'll call that delta A. Well, what is that? That's the length of a subinterval in the x direction times the length of a subinterval in the y direction. So that's delta x times delta y. Okay, so call the subrectangles R, I, J. Okay, so this will be the one corresponding to xi minus 1 xi in the x direction times yj minus 1 yj in the y direction. Okay, so there are n times m times n rectangles, subrectangles. Okay, so these are the bases of our boxes. We need the height. What do? In each subrectangle, I pick a sample point. That's the second step. Okay, so choose in each Rij a sample point. It can be any point. So this depends. So it's in Rij, so it depends on both I and j, right? So we'll call it Xij star. Okay. And so the height, so so each box, so a box has height f of, sorry, so I'm missing something. I need two coordinates. Of course, I need a point in the plane. I need two coordinates. Sorry about that. So a box has height f of xij star, yij star. Okay. And base, the base is delta A, right? Or the area of the base, I should say. Okay, so here's a picture of one of these. Let's say this is Rij over here. We have a sample point, which is here. This is Xij star, Yij star, right? And I look at the height of this. This would end on the graph of the function. Right, so that's the value of the function at this point. And the box we're interested in will be, that's a bit tough for me to draw. So it's not curved, right? The box is flat on top. Sorry for the picture, but so that's the box, so that it's approximating. So of course the top is flat. F would not be flat over this small rectangle. Right? So it's not quite the volume we want, but taking the limit, we should be okay. Okay, the question is, since delta x, delta y are very small, can we say that they are equal? Um, um, formally, no. We're going to take a limit, but what is the star for? Yeah, the star is to just let me finish the first delta x, delta y. Okay, so delta x and delta y depend on our subdivision. I'm doing a subdivision. I'm fixing the number of subintervals in each direction that I'm taking. I get a delta x, I get a delta y. We will take a limit. So, uh, so the answer to your question, are they, can we say that they are equal? No. Okay, formally, no. Okay. But eventually, again, so just to finish that point, so delta x, delta y depend on the number of subdivisions. Yes, when n and m are extremely large, delta x, delta y will be very, very small, and we're going to take a limit. But otherwise, no, you can't really suppose that they're equal. Second question, what is the star for? Mark, I'll get to your question in just a sec. Okay, so the star is just is just a name. It's just a notation for the sample point. It has no meaning by itself. Okay, it's just, rather than call it xij, yij, there's a star there just to indicate that it's some point in the subrectangle. It has no specific meaning other than just give a name to that point. Does that answer your question, Marie? Good. All right. Okay. Mark, I don't understand what is the function of xi and yi. My new rope has a height of f of x. I'm not sure I understand your question, Mark. Sorry. Okay. So if I, yeah.
Like in number 2, you said choose in each Rij a sample point,
Yeah.
and then a box has a height of this and this.
Okay. So I'm evaluating f at the sample point, right? So the function f is a function of two variables. I take that point, that subrectangle, and I evaluate f at that point. So imagine that the function is positive. That's the height, right? The graph of the function, the point there on the graph, its z coordinate is the value of f at that point, right? So that's the height of the segment from the xy plane to the value of the function, right, at this point. Yes, great. Okay, super. Okay. All right. So again, you can imagine that the top of the function is curved, but we're taking the value at a sample point, so we get a flat box, right? So it's parallelepiped. We can easily compute the volume of that, right? And it's okay. Y are points xij, yij. Isn't I associated to x and j associated to y? Good point. But yeah, that's actually a very good question. So let's suppose, so the question is this: why does the x star ij have a j there? Because if it didn't depend, okay, so let's draw something. Let's say I have two of these rectangles, okay, for j equals to 1, j equals to 2. I take a sample point here, right? If the x coordinate of this sample point doesn't depend on j, then the next one would have to be also exactly in the same. Is that what am I saying the right thing? I'm allowed to take my sample points anywhere in the small rectangle, right? So this sample point here, it can be any point in this rectangle. So its X and Y coordinates are completely independent of the one in the next box. Do you see what I mean? So the point which is here that I'm taking in this rectangle, let's say Rij, its X and Y coordinates are completely free within this small rectangle. I don't want to have all my points all lined up like this or like this. Do you see what I mean? All right, good. Okay, let me, I'll just leave it there, but okay. All right. Okay, so I have my box. So I have my sample point, Xij star, Yij star in my rectangle Rij. Okay. So the box associated to this has volume, base, area of base times height. The area of the base is delta A, and the height at this point is f of Xij star, Yij star. Okay, so box has volume. I wrote it backwards. I want it the other way. So it's f of Xij star, Yij star, delta A. That's one box. Now I need to add them all up. I have 2 dimensions. So it's a double sum, okay? So let me write it out, and I'll explain a little bit how it works, okay? So, so this is the Riemann sum for 2 variables. So here we go. So this is the sum. I'll write it in the same direction I had in the notes. I equals 1 to m. J equals 1 to n. F of Xij star, Yij star, delta A. Okay, so that looks daunting, but what it is not so bad. Okay, so we add this way. So it's a double sum. So let's take a look at, let's say I have a rectangle like that. Okay, so this is, let's say, let's put the index I here, 1, 2, 3, 4, and the index J, 1, 2, 3, like that. Okay, so how does this double sum work? Just, I mean, for our purposes, we're not going to play with that anymore, but just that you see what this actually means, okay? So first of all, I is set to 1, okay? And then you look at the inside sum, and you sum j equals 1, 2, and so on. So first I is set to 1, and then you add all those from j equals 1 to n. So it means that this is the first one you'll be taking, then this is the second one you'll be taking, then the third. Okay, so once you've run through all the j's, then you increment your I by 1. You go to I equals to 2. So then you move to I equals to 2, and you repeat. You sum for all the j's. So this will be the next one you add, and this next one, and next one. And then I goes to 3, right? So this is how it goes. and so on. Okay? So that's just how you would add them all up. Okay? So first you fix I equals to 1, add all up for the j's. So you're adding that first column if you wish, and then the second column, third column, so on. You could flip the sums, and it would be the same, except you'd be adding rows one after another. Okay, but obviously it would give you the same result. Okay, so hopefully that makes sense. Okay, but all it is just adding all the volumes of the boxes. Okay. All right. So now we can press on the power button of our iPad, or we can move on. Okay, to our definition. So it's the same as the one variable case. So here we go. So we say that f is Riemann integrable if, and now I have to take a limit when both subdivisions get smaller and smaller and smaller. So both n and m go to infinity. So it's the limit. I mean, this is a bit informal, but this is the idea. So if the limit of our Riemann sum exists, okay? And again, we're not going to worry about whether functions are integrable or not. We're going to play with functions that are, but we want to define this properly, okay? So if the limit exists, this is a number, right? And this is called the double integral of f over the rectangle R, and it is denoted by the following. Okay, so you have two integral signs to indicate you have an integral in two variables, and the rectangle is specified at the bottom of the two integral signs. Okay, so this is our definition, formal definition. You can guess that as in the one variable case, we're not going to be computing these things with the definition. It's a mess, right? So hopefully we have another way to do this, okay? Before I stop, because I'm almost done, this is basically what I wanted to do today, okay? Just a couple of remarks. Okay. Okay, so this is our definition, notation. Okay. Okay, so the first thing, if f is greater or equal to 0 over the rectangle, okay, so if f of xy is greater or equal to 0 for all xy in the rectangle, yeah, like that, okay, then we define, this number defines the volume of a solid, and the volume of the solid S, which is bounded by the graph of f, the xy plane over the rectangle is precisely this number. Okay, so that's a special case. As I said, in general, what you have is a signed volume, that's the intuition, but if the function f is, the graph is always over the xy plane, over the rectangle, then this is a solid, that's its volume, that's the way we define it, okay? Second remark, is that the definition for any number of variables is exactly the same, except that you have to subdivide in every single direction, right? Okay, so the question is, what is the difference between this way of finding a volume and the other way that we have learned in Calc 2? That's a good question. Next class, I'm going to exactly show you the connection. So there's a subtlety here. So what I've done here is defined the volume the way that we think volume is supposed to be, right? But from a practical point of view, this definition is not very good. It's just too hard to compute. Next class, I'm going to show you how we can actually compute this, and that'll be the way that you saw in Calc 2, basically, okay? So when you go to higher dimensions, you know how to work for one variable, you go to two variables, say, okay, a way to attack it would be to slice things up in a way that we can use what we know for one variable, right? And that's what we're going to do, okay? So I don't know if that answers your question, but basically it's the same thing, roughly. We'll see the connection next class, okay? Is that good for you? All right, okay. So again, for three variables, the domain would be a three-dimensional box, and the height would give you a fourth dimension, but the principle is exactly the same, and you'll have, let's say, in three variables, you'd have a triple integral over a certain solid of a function, then it would be dv, and okay, so there's really nothing new if you go to higher. It's just a mess to write up, or more of a mess to write up, but it's exactly the same principle. There's really nothing new here, okay? And finally, what's my last remark? Yeah, so well, actually, your question connects to my last remark. So as in one variable, the definition above is not very useful to actually compute. So next class, so how to compute, and so it connects to what you saw in Calc 2, so it connects to Calc 2, okay? And the main theorem is called Fubini's theorem. Which tells you that this integral, double integral that you have, can be computed by iterating one variable integrals. Okay, so it's sort of similar in flavor to partial derivatives to some extent. Okay, you'll see how it goes, but we'll see that next class. Okay. All right. Any questions? That's good. Excellent. Okay, so that's it for today, and I'll see you on Wednesday. Don't forget your WebWorks, but I think it's due next week, right? But anyway, okay. Goodbye. Same to you. Thanks.